We defined wavelets. I talked a little bit about what a definition of a multi-resolution analysis was. I showed you, I gave an example without going through the details about the Haar wavelet. And then I shifted back to Shannon situation, which is what I began this discussion of decompositions with. And I want to go into that more deeply today, and then I'm going to go more deeply into the Haar business. So we've got a long runway, and some of you may think I'm not taking off fast enough, but basically I'm establishing things hopefully very carefully. In any case, so I'm going to make in order to do this nicely, I'm going to make the following definition. Let K be in d-dimensional Euclidean space thought of on the spectral side. Have the property that minus 1/2 d. By that I mean cube around the origin of points. So this is the cross product. Minus 1/2 d times. Okay? I'm going to say we have the property that is tau congruent to k. By that I mean the following. That is, there exists capital KJ's sequence, a sequence of disjoint Lebesgue measurable sets KJ contained in R d hat. And there exists a sequence lowercase kj of integers in ZD. So the cross product of Z with itself d times. Such that the sequence KJ is a partition of K, and KJ plus lowercase kj is a partition of minus 1/2, 1/2. Okay, so partition, what does that mean? By a partition, all I mean is that I've got a set, and I cut it up into finite or countable number of pieces, and those pieces essentially don't overlap except maybe on sets of measure 0, and their union is the set. So this is the first time I use the word partition. Sequence of disjoint sets and integers such that that is a partition of K. So that means if I cut up K into 12 pieces, none of which overlap, and then I, as a jigsaw puzzle, put it back together, then those KJs are a partition.
So the volume of K and the d-dimensional cube is the same?
Yes. Okay, so we're going to talk a lot about this. But let's begin with an example. And this gets us right back to the Shannon wavelet. So example, let K equal to minus 1 minus 1/2 union, 1/2 up to 1. Now, that turns out that that is congruent K is congruent, congruent to -1/2, 1/2. Now this is very simple, but there's a very interesting phenomenon going on here. Why? And the answer is not why not. Why? Because if I take, if I write K minus be -1 -1/2, and K plus, someone shut that door for me if you don't want this, be equal to 1/2 to 1. Then, if I look at K minus and I add 1 to it, then I'm at 0 up to 1/2. So K minus plus 1 union K plus minus 1 is actually equal to -1/2, 1/2. Very simple. And that idea is an idea that goes back to, but it's used by Escher. You see these, Escher pieces of artistry where he starts off with a glump and ends up with a cow or something. But at each step, it doesn't look like he's done too much. Very often, part of his cutting up process is doing exactly this sort of thing, moving pieces. Now, I'm not taking the integers as my lattice, but there are other ways you can do it. And that simple idea, which I've already devoted 5 minutes to, is something we're going to milk. On this particular example, let's also note that 2 to the m k is a partition. Well, let me write it this way. Is a partition of R hat, where M runs through all the integers. And we saw that last time. Basically, multiplying this by 2, it expands out, and this length half, then goes from 1 to 2. And then the next one, when you multiply it by 2, goes from 2 to 4, et cetera, et cetera. And then when you come down with negative values of M, crunches down, you get every number there, except you don't pick up, well, the way I did it here, you pick up, but you might not pick up 0. Yeah, yes, Brian.
I noticed your definition of tau congruency, it seems to be reversed between the example and the definition. Is that?
It is, but it's commutative. Yeah.
Okay.
Sorry. And the use of the word partition, frequently we'll use the word tiling. It has a little more height to it. Okay, so let's continue with this example here. And I want to do a calculation. So C, let psi hat be equal to the characteristic function of minus 1/2 plus characteristic function from 1/2 to 1. Okay? And let F be in L2 of R. Now I'm going to do a calculation for this one-dimensional case, which is going to be easy, so that you see what's going on when I do the d-dimensional one in just a minute. So we're going to take M and N and Z. And now let's look at the integral over K of of I want this to be equal to minus 1 to minus a half of f hat. I'm just doing a blind, unmotivated calculation here, but its context will become clear in about 5 minutes when I do the more general one. Of 2 to the m lambda e to the 2 pi I n lambda d lambda plus the integral from 1/2 to 1 of the same thing, f hat of 2 to the m lambda e to the 2 pi I n lambda d lambda. And now what I really want to do is I want to I want to get in a form that where I'm going to make an interesting change of variables. So this is equal to the integral from 0 to 1/2 of f hat of 2 to the m gamma minus 1 e to the 2 pi I n gamma d gamma. And that's when I said gamma equal, this is my congruence that I'm using here, lambda plus 1. And then plus the integral from minus a half to 0 of f hat of 2 to the m gamma plus 1 e to the 2 pi I n gamma d gamma when I let gamma equal lambda minus 1. Okay, that's just change of variables. And even though it looks like I'm killing it, let's do that. So this is equal to, putting them together, minus 1/2 to a half of e to the 2 pi I n gamma. And then I just want to write this all down as f hat of 2 to the m gamma minus 1 characteristic function of 0, 1/2 of gamma plus f hat of 2 to the m gamma plus 1 characteristic function of minus 1/2 0 gamma d gamma. Okay, nothing mysterious except that I started off integrating over k, and I just wanted to do the change of variables to bring it back to that. Okay? And I could take this another step by writing it down in terms of this is equal to integral minus a half e to the 2 pi I n gamma, and we have then f hat 2 to the m gamma minus 1, just making the change of variables at characteristic function of k minus of gamma minus 1. Okay. Just by making the change of variables. Not very exciting, it seems. Plus f hat 2 to the m gamma plus 1 characteristic function k plus gamma plus 1. Okay, now I'm just asking you to hold on to that calculation because I'm going to look at a slightly jazzier version of it in a couple of minutes. Well, I ended last class, so end of this example. I ended last class by stating a theorem, which is basically the Wavelet theorem. And the theorem says the following. It says, let's consider that k equal minus 1 minus a half union 1/2 1. And define psi as before. Psi at equal characteristic function of K. Then psi mn, the wavelet system, is an orthonormal basis for L2 of R, where if we just take the inverse transform, we have that psi of t. Oh, by the way, sorry, I've got to make the adjustment here. I could take gamma omega equal to half. That's correct. So, now how are we going to prove that? The way we're going to prove that is and some of these things I noted last time. So, proof. Always be suspect when a person puts this quotation marks around the word proof. Psi m n is orthonormal. Asserted last time, I'll bad way of putting it, but it's probably also an exercise, but it's just a calculation. Then we have that result from functional analysis that I mentioned last time that we'll actually prove next week, and some other things in functional analysis, just to see what we need in functional analysis in this course. If you're in a Hilbert space and En is orthonormal, that implies that En is an orthonormal basis for H if and only if that for every F in H we have that sum F En quantity squared is actually equal to the norm squared. Okay, so that's just a standard Hilbert space fact, and you'll see next week when we talk about functional analysis that it's more or less routine. And so, in order to prove the result, we have to prove, let's call this one. Therefore, to prove the theorem, we have to prove one in the case of psi mn contained in L2 of R. That's our H. Okay, so instead of proving that, let's prove something more general. So that's why I have the quotes here, because I'm going to prove something more general and then be able to state something more general. So instead of proving this, let's do something a little fancier. Okay. So assume the following. Assume the following three hypotheses. One, K contained in R at D is tau congruent to minus 1/2 to the 2. Let's assume that 2 to the m k is a partition of R at D. And 3, let's assume that the measure of k is equal to 1. Well, just to pause for a minute before I do a legitimate computation. If you think about those first two, it's entirely counterintuitive. And the first one says that if you have a tiling of a floor like ordinary tilings, say squares are side-by-side typically, but they can do other things, and then row-wise and column-wise. That's a partition of the whole of R2. And if you can do this, that's the same as saying you have a tiling like that. But that says you have a set K like that. Well, let's, just to fix ideas so we don't get too fancy right now, suppose K is just a square in R2. Then it's certainly congruent to that, if it has measure 1. And then you can tile all of R2 with those squares, by moving them around, translated by 1, right? No mystery so far. The mystery is part 2. I'm saying I've got a set here, which for illustration I said let's assume it's a square. But I also want this to be a partition, a tiling. So it can't be a square, that's where I have to do this. Let's assume that these guys here are a partition of R2, say. Now that is mind-blowing because that says if we're just in R2, that it has to be like an annulus. And so I'm saying, let's say there's a set that satisfies both those things. They're square tiles and they're annuli. And you might think that that's doubtful. So after I do this calculation, I've got to do some convincing to you that such sets exist. But for now, let me, and no reason to trust a man over my age, but let me assure you that such sets do exist.
Oh, so we've already shown one, right? I mean, the K was the one that we've shown explicitly was such set, right?
In one dimension.
Yeah. Oh, okay. So you're saying it's harder to believe in the higher dimension.
I personally think it's harder to believe in higher dimensions.
Yeah.
We can take a vote. So, yeah, one dimension. It's
Is it everything is that the volume of K? Is it
yes, the area of the water.
Just redundant.
What's that?
That's actually
Yes. Okay, now so let me do a calculation first, which is just nice calculus, and then we'll talk about the existence of such sets. But please don't ponder their existence right now. Just act as if you're excited by this calculation you're about to see. Okay? I mean, even when you're nodding off, just say, oh, wow. Okay, so let's take F in L2 of RD. And basically I want to take psi hat to be the characteristic. Boy, once I get this fixed, I'll be okay, I hope. I want to take psi hat to be the characteristic function. That. And so if we look at the following, we are going to look at the sum of f psi mn squared. And I'm summing over all, see with the wavelet systems in R, I was just taking all m's in z and all n's in z. But this operation really is just for z, whereas translation is for zd. So my sum here is really for m in z and n in zd. And maybe I should make a point of what that really is. So this is just an aside. Psi m n of gamma is equal to, in this dyadic case, 2 to the m d over 2 psi of 2 to the m gamma psi hat. Excuse me, x. X minus n. So you see you need the n's being zd, but the m's are relegated to z. Okay, so if I just do the calculation now, that comes out to be, by using Parseval. Question?
Yeah, you said there's 3 assumptions, but what's the conclusion? What are we trying to prove?
Oh, what I'm going to prove is I have these 3 assumptions, and I'm going to calculate this.
It shows that it's f squared.
And I'm going to show this the norm of f squared. And I actually, yes. But there's some work involved. Well, let me. So we're going to use Parseval right off the bat. If I write this down, this is an integral on the space side. So when I go over to the frequency side, I have the sum over all m's of 2 to the m d. And then the sum, I can't believe I think I made a calculation when I'm looking at here. Let's see if I can get myself out of it. So let me put the m's and the n's here for a moment. And I'm looking at that absolute value, and I pulled out the 2m over 2 times d squared. And then I have the integral of f hat of gamma e to the minus m d e to the 2 I n to the 2 to the minus m dotted with gamma. Not quite done yet. And then psi hat of 2 to the minus m gamma conjugate d gamma squared. Okay, because when we take by Parseval, that integral goes into, this is a conjugate over here when I write it as an integral. This goes into f hat of gamma, and then I just have to take the Fourier transform of that guy there, and the Fourier transform of that guy is going to, this comes out of a constant that comes from here, but then I still pick up another constant when I take the Fourier transform of that, just by the dilation that goes on again. Okay, so there I've used the Parseval thing. And now, just simplifying a little bit, this is equal to the sum over all m's of e to the, 2 to the md. I'm squaring that other one, minus 2md. And then I have the sum over all n's of the integral, summing over all of r d, of course, hat, f hat of gamma, e to the 2 I n over 2 to the m gamma, dotted. That's a dot because the n's are also vectors. Psi hat of 2 to the minus m gamma conjugate d gamma. Yeah. That's magical if I did, isn't it? I mean a 2. Yeah. Because I take the Fourier transform of this, and when you take the Fourier transform of that, it's a scaling factor because of the dilation. Okay. And then this is equal to, I have a square. And then this is equal to the sum over all m's in z and n in zd of 2 to the m. I guess I want to minus m. And then where I am now is, oh dear. Stop the camera for a minute. I have to swear.
Professor, what do you mean by n and z?
So this is, n and zd means n is an n, a d-tuple of integers. And j's and, okay. Oh, I made it. Sorry. So this is okay. And now I, you can turn it back on, or else it's already been on. You never shut it off. As long as you don't show it to the dean. Okay. So this is equal to, by making a change of variables, but I'll get even right. F, the integral f hat of 2 to the m lambda e to the 2 I n dot lambda psi hat of lambda conjugate 2 to the m d lambda quantity squared. And so that means that I can write this down when I square that out as the sum over all the m's in z and n in zd of 2 to the m d. And now I have my integral over k. Because of that change of variables. And I have f hat of 2 to the m lambda e 2 I n dot lambda d lambda quantity squared. Okay? Now I'm going to use my tau congruence. And because of the tau congruence, and because of this calculation here, but for d dimensions, that's why I did this calculation, because all I'm doing now is something a little more complicated that after Brent wouldn't shut off the TV camera, I will never do again, of course, because there are certain things one has to do in the privacy of their own boudoir. So I'm leaving out the more complicated calculation. But that was an attempt at humor, but I think I completely botched it. Okay, so this is equal to by this calculation I actually did in one dimension. This is equal to the sum over m's in z and n in ZD to the MD. And I can get my integral now over minus 1/2 to 1/2 to the D, the torus, which I can identify with RD mod ZD, of E to the 2 n dot gamma times this mess, which is those sums of the translates of the characteristic functions that I actually had here in this board in the one-dimensional case a minute ago. In the case of the d-dimensional case, it looks like this: sum over j's of the f hat of 2 to the m gamma minus kj, that's the partition integers in ZD, and then the characteristic functions over the partition sets kj of gamma minus kj, and then this is d gamma, and I'm squaring this guy. And let's call this function in here, just so I don't have to write it over and over again. Let's call this function g, which depends on m, okay, of gamma. So that's a completely believable calculation, which I definitely did. And it's just going to the d-dimensional case of the calculation I did explicitly for one dimension. Now, this is fascinating because now I can use Plancherel again. And so by Plancherel, see, I'm summing over m's and n's. But this is equal to, by a sum over m in z, I have this 2 to the md, as before, of the integral over the minus 1/2 to the d, where this function is defined, of g m of gamma squared d gamma. And why is that? Oh, what that says is the following. That's one of the things we did the first day of class. That says that the Plancherel formula for Fourier series, when I extend this function periodically over the whole of R hat D, that says that the Plancherel theorem for Fourier series, which actually is Pascal's theorem, says that the L2 norm, squared in this case, is the sum of the Fourier coefficients. So that's exactly Parseval. I mean, it's so messy it's hard to see, but that's what it is. And now I'm going to return to doing a change of variables. So I had to use Parseval twice in this proof. Now, by change of variables again, this becomes equal to, I mean, I can go backwards. This is equal, I want to go back to k. I mean, I got to go on this group here, this compact group, in order to use Parseval. My business is really on k. I'm just going to translate that. And so this turns out to be equal to the sum over m, infinite m, of 2 to the m d, the integral over k of f hat 2 to the m lambda squared d lambda. You put all these things back together again. It's going one way and then the other. This is what you get. Well, now let's make another change of variables, because how am I going to compute it in its present form? And if I do that, then this just becomes equal to sum over m in z of the integral of 2 to the m k of just change of variables. And that's just change of variables. But hark! Basically, this now, since this is a partition, is just equal to the L2 norm of F squared. So I made assumptions to make this calculation work, and the assumptions are sort of mind-blowing in greater than one dimension. Yes?
You just punch it out right there as well.
No, here I'm just using the fact that I've got these disjoint sets.
So then you want to write with the hat there
But that would still be F hat, which is half.
at the end, very end.
Oh, it's also equal to F, yeah.
Right.
Yes. But here I'm still at the F hat level since I'm on the Fourier side. And so that's why it's equal to this, but I'm not sure. Okay, sorry, I didn't understand your question. So that's my question. So we didn't do anything difficult, but we made extraordinary assumptions. So, and before I talk about those assumptions in some detail, and before I erase this board, which has to do with homework, Nate sent us homework over the by email, and there were the new problems I put in and the old ones he renumbered fine. So I just wanted to make sure you understood this was. Some of these I may not have assigned before, but this assignment may include some of the ones from last time too. Plus, there's a new problem, Z, which Nate will incorporate into the next time you get homework. Okay. But obviously, you haven't seen that yet, so you can't do that. And then for the topics that I want you to start looking at, because next time you're going to get a copy of the bibliography for a lot of books, but also these two journals are the major two journals in the area, in our field. It's a huge field, by the way, because it does intersect with signal processing and image processing, pure harmonic analysis, the whole spiel. And a lot of things going on in dimension reduction. It's a big, big field. But the two major journals are ACHA, Applied and Computational Harmonic Analysis, and JFAA, the Journal of Fourier Analysis and Applications. So start looking through those to see if there's any topics that interest you. You want to challenge yourself, right? And then, besides the homework problems that are due at the end of the semester, I would also like for you to pick out one of these articles and go into it in such a way, expand on it, exposit it, and so that what you deliver to me convinces me you understood some of the salient ideas. Okay? It doesn't have to be 100 pages, 5 or 6 pages. Okay. Now, we also know that, so we've proven the thing we wanted to prove that is very, very important in order for us to use this Hilbert space theorem. In order for us to say something's an orthogonal basis. So for this particular function, where psi hat is equal to characteristic function of k satisfies these two things, these three things, we have proven this, and so we will have proven that this is an orthogonal basis, as to say the psi mn for L2 of Rd, once we prove that these guys are orthogonal. I mean, we have to have, right? That's the logic. Maybe I'll leave that as a homework exercise, because that, in light of what we've done, that's easy. So why don't you write that down as a homework exercise, maybe?
Sorry,
I'm sorry?
what do you want me to do?
I'd like to have you write down as a homework exercise, prove that the psi MNs are orthogonal. Okay? Once you have that, once you've got that the psi MNs are orthonormal, we invoke this Hilbert space theorem that they form an orthonormal basis for the Hilbert space we're dealing with, which is L2 of RD, if and only if this holds. But we just proved this holds. Okay, so, and proving this orthonormality is, it's not difficult. It's just, okay? Not unreasonable. And so, summing all of this up, then we have the following theorem. Let K in R hat D be a Lebesgue measurable set. And if you don't know what that means, it's not relevant. Just think of any bunch of sets that you know and like in RD that are not, they don't have to be fancy. Such that the area, or the volume of that set, is equal to 1. The sets of the form 2 to the mk is a partition or tiling of RD. And 3, K is tau congruent to the unit Q. That is to say, well, that it forms a tiling partition of R. So the integer translates all the form of partition of R, so of RD, but I'll just write it the way we already did it. K is tau congruent to minus a half, 1/2. So let's let K have that property, which is incredibly counterintuitive for D bigger than 1. Set psi equal to the inverse Fourier transform of the characteristic function of K. Then psi mn is an orthonormal basis for L2 of RT. So the big question is, are there such sets? And we wouldn't have wasted as much talk if there weren't, or your time away. And in the homework, I've got, actually I'm not sure if I have this as an exercise. I'm gonna write this exercise down, because it might not be in the homework. Let's formulate the following problem, and also type it in. So A, if K equals -1 minus a half union 1/2 1, so it's the one-dimensional guy. Prove that psi equals the inverse Fourier transform of the characteristic function of K is a wavelet generated by an orthonormal, generated by an MRA, which we defined last time, of L2. And I already showed you how to do that last time, in the sense that we can compute that inverse Fourier transform, which is going to be a different sum of a difference of Dirichlet functions, and then you can prove that's an MRA. However, prove that if D is bigger than or equal to 2, and the conditions of the theorem hold, then by the theorem it is an orthonormal basis. They are of the wavelet form, but then psi equals the inverse Fourier transform of that characteristic function is not generated by any MRA of L2 of RD. And there are other parts to this that I will not write down. Basically, in one dimension, this phenomenon, well, for the so this is comes from an MRA, but Journet constructed just a slightly more complicated set on the real line that doesn't come from an MRA, and that's already in the exercises, I believe. And then if you go into higher dimensions, the sets that you get for which these are wavelets are very, very complicated. People say, oh, they look like fractals, but they're not fractal. Very complicated looking. And none of them comes from an MRA. And just as a matter of fact, this whole phenomenon was discovered by David Larson, at that time a student, very fine mathematician, died, and then Darren Spiegel, and all this activity took place at Texas A&M in the early 1990s. And the way they came across it was, it's one of these great things. They were all, at that time, doing C-star algebras. This is not C-star algebras. Basically, they came in, and they were not even wavelet specialists, because the specialists would have stayed away from this problem because people felt that almost everything had to be an MRA, and the Journet example was maybe just sort of a funny aberration. But their results were in some sense abstract. And so a number of us wanted to construct them. And so we did. They're very, very good, systematic, fairly general constructions of these things that you can actually put in a computer and make them. But they are definitely counterintuitive, these three hypotheses. Counterintuitive. Okay. Now, what time is it? Mr. White. What's that? Oh, thank you. All I have to do is read the clock. Okay, so now I'm going to switch gears, and so we've back to high, and the higher wavelet, if you recall, we're just on the real line now. We defined this function, which is essentially what Hag did back in 1909. And that function there, psi mn, is an orthonormal basis for L2 above. And this is the wavelet. So, the one we've just been looking at is we're looking over here on, let me take the frequency domain since I can draw it more easily. We're looking at the function from 1/2 to 1, and then minus 1/2 to minus 1. And this will be called psi hat. And then for that psi hat, psi mn is an orthonormal basis for L2. And this is the name we gave either Shannon or Sink or Littlewood Paley wave. So.
The Shannon dyadic wavelet.
Oh, I'm doing everything diadetically, yes. So far, I have not said anything that's non-dyadic. When I write this, I just mean, until now, psi mn of t is equal to 2 to the m t, psi of 2 to the m t, right?
So what does dyadic mean?
Oh, because of the twos.
Oh, okay.
Powers of 2.
So we can use a triadic or something?
Yes, yeah, in fact, there's been a lot of things done when you can use rational numbers, when you can use irrational numbers. It's it gets rather complicated.
So the purpose of using dyadic is because the easiness we have in implementing filter banks?
I think it was because it was the easiest thing to do. So that's a very good question, because the way the history of this thing arose, the filter banks people in the 70s, basically did the hardest part of the proof of the MRA theorem, which we're going to be talking about pretty soon. The image people understood the structural part of multi-resolution analysis just a couple of years later. And it is true that the speech people were doing dyadic because that's how they did their coding. So I guess that was the driving force, you're right on that. But clearly, when you wanted to go to higher dimensions and you want to look at non-separable filters in higher dimensions, essentially non-tensor product, then all sorts of other ramifications arise. And the dyadic is still a very interesting case, but in, say, in d dimensions, that just gives rise to a matrix with 2's down the diagonal. But the point is you can use all sorts of other matrices to wavelet theory. And in this course, I'm not going to go into that too deeply, just to let you know it exists, because I want to cover thoroughly some of the basic issues. Now that's, I view that as something, once you understand the dyadic case, that's pretty simple, even though it looks very, very impressive. Okay? Question? So I view these as sort of antipodal, because here we have basically step functions, and so we're going to get very bad decay in the spectral domain, and with sinks. And here, these are step functions, so you're going to get very bad temporal localization over the time domain. Here you have very good temporal localization. So you're trading off. So they're like two extreme cases. And so I'd say we've really done a fairly thorough job on the elementary theory here, even for RD, except for the fact I haven't told you how to make these sets K in RD. If we have time later in the semester, I'll do that. I mean, we can certainly give you lots of references. Here now, I want to do a thorough job on the Haar wavelet, because that also is inspirational to see some of the things that go on in the definition of an MRA. So let me start with that. Even though it's only 7, should we take 5 now and then we'll go for until I stop? So because this is a good breaking